So I would like to thank Michael for the invitation to this seminar. And today what I would like to present to you is some results relative to the convergence of certain series representing 2-point functions in specific instance of a 1+1 dimensional quantum field theory, the Sinh-Gordon model. So this theory is rather special among all theories because it is integrable, which means that there are powerful algebraic techniques allowing you to construct certain building blocks, which then allow you to construct Weidmann functions for this theory. But so far there was, while there were, in a certain sense, closed expressions for the Weidmann functions, the question of the well-definedness of these expressions from the mathematical point of view was still open, since it was given by a series of multiple integral, that is to say, where the n-fold sum is given by a n-fold integral. And what I want to report today is about some progress in this direction in the case of 2-point Weidmann functions. And then if you're interested to see more details, you can find the paper on the archive. So maybe let's start with the outline of the talk. So first I'd like to present the main kind of theorem which I obtained, but prior to that, I'd like to provide at least a certain amount of motivations why it's important to look at such convergence questions. In the second part of the talk, I will focus on the per se application of the theorem to the case of the Sinh-Gordon 1+1 dimensional quantum field theory. So basically, I will review the main results which allow you to construct this theory. I will go through how you can construct this theory through integrable settings and what kind of expressions you get for 2-point functions in this theory. But I would also like to comment on some of the potential applications of this work to pushing further the theory of special functions. And finally, in the last part of the talk, I would like at least to give you some flavor of the techniques and ideas you can use to establish such kind of results. So let me first start by just some elementary considerations, because it really shows very well what may be going on. So in principle, well, when one would analyze some physical problem, then it's very often, for instance, by doing some perturbative expansions, one expresses the answer in terms of some closed expression given by a series. The fact that one is able to push the algebra very sufficiently far so as to be able to write down some explicit expression for the summand of the series may already be a good indication that then the result is well defined and all is fine. But there may be lots of subtleties in that. So of course, if an is just 1/n squared, then there's no problem with summability, and one always gets pi square over 6. But as soon as one ends up with non-absolutely convergent series, like -1 to the n over n, then depending how one sums, even though one can give some sense to the summation, one can get more or less any results. For instance, if one would take a summation with some permutation of the integer, which is dominantly even, which meaning that basically you permute the integers in such a way that most of the time you just get even integers, then if you understand the summation of -1 to the n over n as a limit of a sum where you sum up over such a permutation of the integers first, then basically the sum goes like summation of 1 over 2n, and this blows up. But then if one sums up with the natural order on the integers, then of course one recovers the expected result minus log of 2. But then if we focus on this kind of representations, which leads to minus log of 2 result, you can say that you can represent minus log of 2 as this series, but the representation in terms of a series is not unique. You can have many representations, and actually some representations can be much better than others. For instance, if one would choose in this series to sum up the even and odd terms, put them together, then one would end up with a absolutely convergent series, and this allows you to do a lot of operations on this series. So this is quite important to have absolutely convergent series, because very often obtaining an expression in terms of a series is just the first step. Then one wants to extract some physical meaningful information, and for this one usually performs resumations and many such procedures. So yeah. Now, well, this was in a sense a cooked up example, and one could argue that maybe on some physical systems such situations do not appear, but in fact problems with convergence appear almost well, at least in many instances. Probably the best example is convergence problem while dealing with perturbative expansions in quantum field theories. So basically, if one just does a naive perturbative expansion, what happens is that one ends up with infinities, and this is basically because the summation procedure is not properly convergent. And of course, there's a way to find a good series representation for perturbative expansion, and basically one can frame this under the name of some renormalization scheme, which means to reorganize and sum up appropriately terms in the expansion. Well, this is one of the instances where such problem arise, but then what one could at least try to argue on the first approach, that maybe these convergence problems are related to the fact that in a generic quantum field theory, you don't have a relatively firm algebraic setting which will rigidify you the type of answer you can get. And if you go to some algebraic setting, I mean to some model where there is a deep algebraic setting behind the model, then maybe such problems do not arise. So here I'm thinking about quantum integrable models whose integrability basically is related to the presence of to an underlying representation theory behind the model of a certain highly structured algebraic structure. So here I'd like to focus on one example, the XXZ spin 1/2 chain. If it doesn't really ring a bell to you, it's not so important. Think of it of some model for which you can explicitly compute the ground state expectation values of certain products of two local operators, say one operator at position 0, 0, and one operator at spacetime position xt. So integrability techniques, as pioneered since the mid-80s in the early works of Sinh-Gordon and Karol, they allow you to express such correlation functions as a series of multiple integrals. So a series where the n summand will be some an-fold integral. An is some sequence which goes to infinity with n. Typically, you have an equal n, where you have an integrand which is quite explicit, but usually couples all the integration variables in a relatively intricate way, and it depends parametrically on x and t. And here, well, I introduce one notation which I will use throughout the talk, that letters in bold with a subscript indicate a vector of the dimensionality given by the subscript. So the pioneers of obtaining such representations were Sinh-Gordon and Karol, who managed to obtain these representations for the nonlinear Schrödinger model, the XXZ chain. So then, what I will say is not so much a criticism of their work, because they were really the pioneers of these things. So many things at the time were still not clear. But so what they were trying to do once you get such an expansion is to extract some physical information out of it. So in the case of the XXZ spin chain, because you have some application to universality, so long distance and long time asymptotic behavior of 2-point functions, you may want to try to extract this from such a closed expression. And this is what Isergin and Kripin were attempting to do. So what they were doing, they were splitting the series, doing some resumations, exchanges of symbols. They end up eventually into some form of series, and they arrived into some concept of asymptotics, which was basically contradicting conclusions of universality. And then the only way to get out of this problem is that actually at some point one was ending up with ill-defined non-convergent series. So it can definitely, such problem can definitely happen in quantum integrable models. In fact, since that time, I think there are quite a few examples of still ill-defined series in quantum integrable models. So this is kind of a motivation to try to rigorously frame their convergence properties. One case maybe I can single out here is that convergence is actually okay if one considers the most simple model of most simple quantum integrable model, which is a free theory. In this case, basically correlation functions are expressed in terms of Fredholm determinants. So it's again series of multiple integrals, but you have techniques to show how this series converges. Whereas in the general case, you have to find a way how to bound the growth within of the n-fold integral appearing in the n-fold sum. In fact, the only proof of convergence of such a series of multiple integral goes back to the works of Fedosmenov in the early 90s, where he was able to prove the convergence of a two-point function arising in the Li-Yang model. So okay. Now,
I'm sorry, Karol.
Yes.
Was it published by Fede?
No, it's an unpublished work.
Okay, and second question: what about Ising model?
In the Ising model, there is no problem, because basically the Ising model is related to a free model. It's a free fermionic model. So
this is Sinh-Gordon determinant point.
Yes.
Okay. Thank you.
So now maybe kind of the overall setting where this developing techniques for proving convergence sets in is the overall goal is to try to set up some techniques which would allow you to statutate on the convergence of such various series of multiple integral representations for the correlation functions in truly interacting quantum integrable models, which were obtained since the 80s in the literature. So actually there are two classes of such models. The first one would be interacting integrable 1+1 dimensional quantum field theories. So the Sinh-Gordon model, but more importantly, Sinh-Gordon models and many others, but also integrable lattice models like the XXZ chain or other models. And in terms of complexity of the series representations, maybe the first series are slightly less complex. So it's good to attack the problems for the integrable quantum field theory case. Good. So after this introduction, maybe let me just present the kind of technical result I obtained. So and then I will connect it with the Sinh-Gordon model in a second part. So I was interested in the following n-fold multiple integral. So this integral will arise as the n summand in the series representation for a two-point function in the Sinh-Gordon model. So it's an integral where one integrates over n variables beta 1, beta n, running through R to the n. There's some combinatorial normalization 1 over n factorial 2 pi to the power n. Then there is a one-body confining potential, e to the minus r cos beta a minus alpha sinh beta a. So this potential arises for each of the integration variable. Then you have a two-body interaction between the integration variables, which couples couples pairs of variables beta a minus beta b and depends on the difference. So for the Sinh-Gordon model, the two-body interaction potential, you have a closed form for it in terms of its Fourier transform. It's actually not so important for the details of the analysis. Maybe, I mean, the precise formula is not so important. What is important is like the overall shape it takes, which I have plotted here for some specific value of the parameter b here, which will be between 0 and a half, and b half, its complement 1/2 minus b. The typical shape is the same when b runs between 0 and a half. And what are the features of the potential in two-body interaction potential is that it goes to 0 at infinity, and close to 0 it has it goes like logarithm of its argument to minus infinity. So which means that e to the half w beta a minus beta b has a 0 of order 2 at beta a going to beta b. And finally, there is this third component of the integral, which really corresponds to a non-trivial coupling between all integration variables. It's given by the modulus square of a function kn of p, depending on all the integration variable. And this multi-body interaction is given by a combinatorial sum. So first, one sums up over vectors ln, which components la being equal to 0 or 1. There is some sign prefactor, -1 to the LA. Then there is some combinatorial factor which couples all the integration variables. It has a pole at beta A equals beta B. And some dependence on the parameter b. And this multi-body interaction, they also involve some function p, which depends on the integration variables beta n and summation variables ln. So first of all, the integral is well defined for any beta a and beta b because, as I said, the two-body interaction has a double 0 at beta a goes to beta b. So this kills the poles present in the kn of p. And further, kn of p is basically bounded function of the betas. The w is a bounded function. E to the half of w is also a bounded function. So then the convergence of the integral is ensured by the very strongly decaying potential at infinity. Okay, and now the question is, how does all this behave in the large n limit? So if one makes a very mild assumption on the growth of the potential of these functions p, which appear in the multi-body interaction k, so if one assumes that they are bounded in n, like some constant to power n, and then has at most the exponent of a polynomial growth at infinity when some of the betas goes to infinity, then, so this again does not poses any problem for the convergence of the integral because of the exponent of a hyperbolic cosine convergence. Then if you have such a property for the Pn, for any kappa 0 which corresponds to the combination of for any kappa 0 positive, if you fix kappa as r times 1 minus alpha, so these were the two parameters appearing in the one body confining potential, and this is basically kappa strictly positive is the regime where this potential is ensures the convergence of the integral. So if you are in such a regime, then the series of multiple integral converges, and one can show the following upper bound on the n-fold integral. It will basically decay with n as a slightly sub-Gaussianly with the correction of 1 over log n to the cube with some explicit prefactor. So in the upper bound for un, there is no dependence on the parameters r and alpha in the leading asymptotics, but it's in the subleading asymptotics. And if you try to send this parameter r to 0 or alpha to 1, then basically the control on the asymptotics gets on the remainder gets worse and worse, and you will not anymore have such a nice bound. And this is okay because you expect actually that something will happen in the series in the limit when r goes to 0. It should have some power law blow up in r. So this is consistent with that. And the second point is, well, in the integral, one would be tempted to say that because there is a 1 over n factorial, this is something which is very strongly decaying, so it should be very helpful for the convergence of the integral. But basically, because this decays Gaussianly, this 1 over n factorial doesn't do much. So yeah, so this is the result, and maybe then I can pass through the connection with the Sinh-Gordon model. So just to review, because I will follow up this strategy. So what one wants to do, one starts from a classical partial evolution equation, where one has some where the field is subject to some potential v, and one wants to quantize these the field and its conjugated momentum. And one wants to do this quantization in data in a way which would be comparable with the scattering data, so the S matrix of the model. And for this, one needs first to propose a Hilbert space on which one will realize the quantum operators, then to realize all the symmetry operations you want to have in your theory on this Hilbert space, and then construct the physically interesting local operators on this Hilbert space, and in such a way that these can form an algebra, so you can give appropriate sense, in particular to the multiplication, even though you would realize these operators as operated value distributions in the space-time coordinates. And moreover, what you want is that your theory be causal. So you need to check that the operators you would construct in this way, they would satisfy causality, namely that the commutator of two fields will vanish whenever they will be space-like distant. And if you manage to do this such a program, then actually what you really want to have is to be able to compare this construction with what you would get in experiments. So get the multi-point correlation functions. And so this is the program now which I will discuss for the Sinh-Gordon model, and in the end of the program there will be the connection to the first result I showed. So the Sinh-Gordon model corresponds to this 1 + 1 dimensional classical evolution equation. You have a D'Alembert operator acting on the field phi, and then non-linearity given by a hyperbolic sinh. There is a coupling constant g and a mass m in the equation. So the kind of advance in the construction of this model on the integrable side was pioneered by Grianic and Vergeles in '76, who managed to give a proposal for the exact S matrix of this model. The reason is that this model is classically integrable, and if one makes if one assumes that on the quantum level you still have an infinitely many conserved charges, as in the classical case, then the presence of infinitely many conserved charges strongly constrains scattering in such a theory, but still doesn't render it trivial, as would be the case in higher dimension than 1. So what Grianic and Vergeles argued is that the Hilbert space of the Sinh-Gordon quantum field theory in 1 + 1 dimension should contain one type of asymptotic particle. So then with this you associate the Hilbert space of the model as a Fock space, so direct sum of L² spaces of ordered R to the n, so with variables β1 greater than β2 up to βn. You can think of this space as elements of this L² of R to the n as containing incoming asymptotic wave packets in the theory. And the Grianic and Vergeles proposed the following form for the S matrix. So first of all, the scattering in this theory is purely diagonal. You just get a phase when two particles scatter, and it's only a concatenation of two body processes. The scattering S matrix is given by the ratio of two hyperbolic tangents of half of β minus I pi b divided by this hyperbolic tangents of half beta plus I pi b. So in particular, it has no poles in the physical rapidity strip located between imaginary part of beta 0 and I pi. And the parameter b is some rewriting of the classical coupling constant g appearing in the classical evolution equation. Well, so then basically one already has the Hilbert space of the model and the scattering data for this model. So then one wants to construct all the quantum operators, quantum fields for this model. So first, one realizes the translation operator in this model. So if one takes a vector in the Fock-Hilbert space, the translation operator will act on these vectors diagonally on each of the components of the vector. So translation operator acting on n-particle wave packet is just a multiplication by a plane wave prefactor involving the two momenta of the particles evaluated at beta 1 up to beta a. Minkowski scalar product with y. So here I recall the form of the two momentum. And then multiplication by the function fn. Now, how one would then realize general operators in this case? So it's a Fock-Hilbert space built on L-square spaces. So one can basically think about realizing operators as appropriate integral operators on this space. And this is at the root of the idea of and then constructing the integral kernels of this operator. It was at the heart of the quantum integrability of this model. So then a general operator, how it will act on a vector? Well, it would produce some zeroth component, some nth component, and etc. Say the nth component will then be just a sum of operators going from the appropriate L-square space of Rm to the L-square space of Rn. And one wants that the operators be invariant in the space-time translation, which means that you can already factor out the x dependence of the space-time dependence of the operator by the adjoint action of the translation operator. So now, how does these integral operators look like? Well, there was really a long quest to determine these integral operators, and it's framed under the name of the Bootstrap program, which is a program which allows you to completely fix the integral kernels of these operators. So it was started by Karofsky and Weiss in 1978, where they proposed at least some framework which allows you to compute the kernels of the operators for the two-particle space. But then, of course, one needs to generalize it to more particle spaces. And this was taken after a very long series of attempts. This was framed by Fedor Smirnov. And also following some ideas of Kamitov and the work of Kirillov and Smirnov. So I will present the Bootstrap program in the next slide. Basically, now how one can write the action of the operator O on the zero particle space, and this is the most important action for the whole construction. So when we act on a vector and look at its component in the zero particle space, so it should be just a number. So what we do, well, we integrate with some kernel the components of the vector in all the L square of Rm Hilbert spaces. So we should sum up over all these components and integrate over the ordered variables. There is an X dependence which just follows from the fact that you have this adjoint action of the translation operator on the field. And then you have the non-trivial part of the action, which is this kernel of the integral kernel of the operator. And then general principles will tell you that this integral kernel actually it's the plus boundary value of a certain meromorphic function in the physical strip. So where the rapidities, each single component of the vector rapidity beta m has imaginary part between 0 and pi. And then, well, more generally, then the action of the operator on the n-particle space, well, it will produce a function of n variables alpha n. And then what you do, well, you do this kind of same sum over all components of the vector, with which you act with an integral operator which brings L square of Rm to L square of Rn. So then you have again a factorization of the X dependence of this operator, and then a non-trivial kernel, which depends on the integration variables beta m and the outer variables alpha n of the function. Now the bootstrap program tells you how you can compute all these functions. So first, the integral kernels for the n particle space, so this mn of alpha n beta m, they satisfy a certain induction relation, which basically allows you to reduce the number of outer variables in mn of O, and ultimately you can solve this induction. I don't give the formula here, but the idea is that you can inductively construct the general kernel m of alpha n beta m in terms of the kernels on the zero particle space, this fm of beta m function. So basically the first axiom tells you that you only need to know the action on the zero particle space, and then the rest of the axiom tell you how you can compute this action. So so the axiom tells you that, well, these kernels should be, in a certain sense, compatible with the scattering. So if you exchange two particles in the arguments of these kernels, then you should get the prefactor, which is given by the S matrix of the distance of the exchanged rapidities. Then you have some axioms which tells you what happens when you continue analytically the function up to the strip, up to the real axis shifted by 2I pi. It's a sort of Riemann-Hilbert problem axiom. And then you have an axiom which tells you how these form factors behave in terms of meromorphic functions. So where are their poles? In the case of the Sinh-Gordon model, there are no bound states. So the only poles are kinematic poles, which arise at rapidities shifted by I pi. So if you have two entries of this integral kernel which are shifted by I pi, then you have a pole at those rapidities with some explicit form of the residues. Maybe, I mean, the precise form of the equation is important when you want to solve them, but otherwise just the main message is you have a certain closed system of equation, which actually, because there is integrability at the root of the model, because you know the explicit form of the S matrix, which is just a concatenation of two-body processes, you can find a closed formula for the solutions to this equations. And in a certain sense, you can interpret it on a physically these equations as being some form of consequence of the LSZ reduction formalism. Okay, so actually.
Sorry. Naive question. This axioms like look a little bit like quantum Knyzhnik-Zamolodchikov equation. As far as I know, people sometimes even call them like this.
Yeah.
Yes. So why here is this? Okay, maybe it's like very naive question, but why here this axioms like relatively easy to proceed? Or I don't know. Like it was telling like it's like easy to proceed. Yes. And there are so much problem with them in integrable system like XXZ.
I think because well, I mean, to derive these axioms in this case, it follows from this basically LSZ reduction formalism. Which builds on the fact that the theory is relativistically invariant, and in lattice models like XXZ, you don't have this kind of tools. So that's why you wouldn't get such a simple characterization of form factors. I think that's the main reason. But still, I mean, one has to stress out the amount of time and effort it took to actually formulate those axioms. So some of the axioms were appearing like quite naturally, and this is the axioms which were proposed by Karofsky and Weiss. But then it took like, I don't know, 6 years of very heavy calculation and analysis to Fedor Smirnov to finally be able to identify the other appropriate axioms for fully characterizing the kernels in the general case. And of course, well, today there are many ways, like to a posteriori justify the presence of these axioms and how they pop up. But I would say that a priori, it's not clear at all that such axioms would work.
Yeah, it's more a question about like why it's easy to get the answer using these axioms, because its exact model, these axioms can be actually formulated like in very physical level, and it's not a problem. The problem is the solution usually.
But I wouldn't say it's easy to get the answer.
So it's still very complicated. It's
yeah. I mean,
because you have to talk very quickly, and I like make that it's very easy step, just solve it. It's not.
No. I think it took really long time to develop appropriate techniques. In the case of the Sinh-Gordon model, there is a simplification because you have a scalar S matrix, but as soon as you go like to Sinh-Gordon, you have the S matrix is already matrix valued, and I mean that now there are techniques, so you just follow a technique for solving it, but it definitely took quite some time to.
So it's still like multiple integrals and so on in the answer, not like some simple expressions.
Yes. So in Sinh-Gordon, you don't have, you have just discrete integrals, so sums. But as soon as you go to non-trivial, like really matrix valued S matrices, you have integrals and combinatorial answers. So.
I would like, maybe I'm wrong, but Arthur, I have an idea that Jimbo and Miwa and their company definitely looked for Feder's form-factor axioms to construct the QKZ. And of course, integral representation for correlation functions in XXZ and integrable representation for form factors in Sinh-Gordon by Lukyanov are very similar. Of course, they have similar structure. We're not discussing the descendants. Descendants is a different story.
I just thinking about work of Jimbo, Miwas, Smirnov, and Boss, where they have this hidden Gassman structure, all these complicated things, and here it was
but this was
just solve these axioms and we get the answer. And I was sure that it will be like two lines formula. Sorry, just
no. But definitely, I agree that in the works of Jimbo Miwa on form factors and like elementary blocks in the mid 90s, there was a very strong inspiration, like especially from the free field construction of Lukyanov, and then trying to get the system.
The efforts with this, yes.
So like in this transparency, well, what I wanted to say is precisely this, that it took quite some time to develop solutions. Like, well, some first solutions were got by Karofsky-Weiss, then Fedor Smirnov developed really substantial amount of effort to produce solutions, also in collaboration with Kirillov. Kind of the first solutions were proposed by Zamolodchikov for the Liang model, which is really what you could think as the simplest truly interacting integrable quantum field theory. And basically how goes the construction? So first you want to get rid of these two axioms, like put them in a more symmetric form. So what you do, you try to solve for these axioms by changing unknowns in the form factor axioms. So first you produce a prefactor. You look for form factors in the form of a prefactor, which is a product of a function of the difference of two variables beta a minus beta b, which satisfy a simple scalar equation. So f of beta is the S matrix times the S matrix is f of minus beta, and f of minus beta actually gives you this two-body interaction, which I shown in the beginning of the talk. And then there is non-trivial part Kn of O. So the first proposition for Kns of O was for this Liang model by Zamolodchikov, who gave in determinant representation. This was then generalized to Sinh-Gordon by Fring, Musado, Simonetti, and Kubek-Musado, again by determinant representation. Then Lukyanov came up with his free field approach for solving bootstrap program equations, and in particular with Brashnikov, he gave some expression for Kn, and then Kn's are realized as average of certain products of free fields, average in an appropriate representation. Then Fagin and Lashkevich and Pugai, they produced a sort of extension of the free field construction, where they managed to construct not only primary operators but also descendant of operators and characterize them in a certain way. And maybe the kind of construction on which I will focus, which is actually a way of rewriting the free field construction of Lukyanov, is the construction which was proposed by Babujan, Fink, Karofsky, and Zapetal for the Sinh-Gordon model in '99, and then which was kind of extended to the breeder sector of Sinh-Gordon, which is equivalent to Sinh-Gordon model by Babujan and Karofsky. And then the idea is to look for this Kn of O, so this non-trivial prefactor, in terms of a certain transform of a set of functions Pn. So I shown you this transform in the first transparency. And the idea here is to look for this transform in such a way that the equations for the Pns are as simple as possible. So basically, if one follows all this line of thought, then, for instance, you can construct form factors of the exponent of the field in the following form for the Sinh-Gordon model. So basically, you produce solutions to the bootstrap program. So you have this prefactor product of some explicit function f of the difference of the variables beta a minus beta b, and then this Kn transform. So this combinatorial sum I shown here, which acts on a very specific function p, which for the exponent of the field takes the form of a normalization constant to the power n, and some factor depending explicitly on gamma and on the summation variables LA, which were appearing in the transform, but no beta dependence. And then if you want to construct other operators, be it descendant of the field or some other operator you would like, then you need to look for other Pn functions, and you have a certain quite extensive list of such functions. Okay, good. So then there is a closed expression for the integral kernels of this operator. So you can compute the Weidmann functions of the theory. And in particular, if you go to the space-like regime, so if you compute the vacuum expectation value of a product of two operators, or for which you can compute the form factors in such a form, maybe with some different Pn function, and if you suppose that the operators are self-adjoint, then what you do basically, well, you first map the vacuum with the first operator to some n-particle space, and then you take the n-particle space with the other operator and you project it on the zero-particle space, and you look at the contribution to this. So what does it mean? So technically, it means that you have to sum up over all intermediate n-particle space arising here. You should have to integrate over all rapidities of particles forming this n-particle space. The action of this operator will produce the kernel FNO at the beta n. And by the other axioms of the theory, you can compute what is the kernel of this operator connecting the zero space to the n-particle space. And it's given by the same function Fn, but evaluated at reversed rapidities. So instead of the vector beta n going from beta 1 to beta n, the components go from beta n to beta 1. And you have to shift everything by I pi. And then you have this oscillatory exponent coming from the x dependence of the second operator. And then, because you have some translation invariance of your integration variables, so such form factors are actually, if you shift all of all the components of the vector at which it's evaluated by the same number, it's invariant under such transformation. So it's a sort of invariance of your theory through Lorentz transformations. And so then what you can do, actually, once you do this, you see that the integrand is symmetric. You can symmetrize the integrand. You can move and deform contours in the integration plane. And then basically, once you deform contour and move to the real axis plus I pi over 2, or minus or plus a pi over 2, depending on the sign of the x component, you change this oscillatory decay of the integral into some very strong decay. And then what you get exactly is that 2-point function in the model are given by the series of this integrals un I shown you before for a specific choice of parameters r and alpha. I was telling you. So then, well, because there's a clear-cut now result how these UNs grow with n, at least for the space-like regime, you know that 2-point function representations is absolutely convergent. So what the estimate, and yes, and in the theorem I showed some technical assumptions on the functions Pn. But actually, these technical assumptions, they seem to be always verified by the classes of P functions which are used in the Sinh-Gordon model. So what the analysis tells you first that the n summand of this series basically decays with n like a Gaussian. So it means it's an extremely fast convergence of the form factor series. This is something which was observed in the past through numerical analysis of such series. Basically, the idea was that even if you take the space-time difference, the Minkowski norm of the vector xt to be relatively small, still you need to sum up just very few terms of the series, maybe first 3, so 1-fold, 2-fold, and 3-fold integral, and then you get extremely good precision. So this confirms or explains why numerics were working so well. The second application actually of this analysis is that well, really to statutate that one has built through such a procedure an acceptable quantum field theory is that you have a local commutativity theorem in the sense that your quantum field theory is causal. So you need to have commutators of space-like separated operators to vanish. Smirnov and Kirillov developed a setting which allows to do it, and they basically have a proof of that under the hypothesis of convergence. So basically, the techniques I developed for proving convergence of Weidmann 2-point functions, they also apply to this case. So then this is fully rigorously settled also. What still remains to investigate is to look at convergence in the time-like regime. This is technically different because you have to regularize the integral in a slightly different way than in the space-like regime, but I think it's doable. And then to look at convergence of multi-point functions, then in that case, the integral representations for multi-point functions are a bit more involved than in the 2-point function case. There's a bit more combinatorics, but also I think it's reachable within the method. Okay, so this is about all I wanted to say about Sinh-Gordon model, and maybe before giving you at least a... I'm
sorry, Karol, could you repeat, please? Okay, no. Everybody knows numerically everything converges excellently, but I thought your statement was to prove that analytical, or how to say, mathematical, there is a theorem on convergence.
Yes.
So say on this, transparent something on this, or it will be later?
No. Sorry. So maybe let me come back.
Please.
So we have this 2-point function.
Maybe I didn't catch.
Yeah. So we have this 2-point function, and it's given by a series of un functions un of this variable m times modulus of x and the ratio t over x. So t over x is smaller than 1 in modulus in the space-like regime, and then m times x is big, is whatever you want. And this un of r alpha are given by this n-fold integral, which is defined for any r strictly positive and alpha lower than 1. So these are exactly the same UNs which appeared in the expansion for 2-point function. And then the bound which I can establish for this UN of r and alpha, provided r is strictly positive and alpha lower than 1, is that when n grows, it goes slightly slower than a Gaussian with n. So of course, then this upper bound tells you that the integral is the series is convergence because you.
So here we see the theory.
Yes.
Point.
Yeah. So then, if one applies this theorem to the 2-point function case with just the p function one wants for the given operator, then you have a convergence of the series.
Okay. Thank you.
And then what I was saying is that because this growth with n, decay with n of the coefficients un is very fast, like Gaussian in n, it's really not astonishing that numerics work so well. It's like a, analytical estimate of how well the numerics act.
So in this point there is a statement, right?
Yes.
About convergence.
Yes.
Un modular. Okay.
Okay, so maybe I can kind of, I'd like also to before giving you kind of the flavor of what one needs to provide the estimate for the growth of this UN. I want to also point in one direction where then this analysis can go, namely towards pushing further theory of special functions. So basically in the theory of special functions, you have a natural grading. So you start with polynomials because they are the simplest, then you take certain appropriate limits of these polynomials, you get transcendental functions. Then if you consider one-dimensional, finite dimensional integrals involving transcendental functions, you get the higher transcendental functions. Say most prominent are gamma function, Gauss hypergeometric function. You have many others. Then if you allow yourself to take series where the n summand is some n-fold integral, you fall into objects which belong to the so-called Pain-Levé class. The most prominent example is the Pain-Levé transcendent. But basically, you can put Fredholm determinants of integrable integral operators in this case, also because they enjoy some specific properties. And then you can wonder what is beyond that. Are there functions, special functions which still we can think of as special functions, but which in a certain sense have a much more complex properties than Pain-Levé Fredholm determinants like. And well, one way to look at special functions is through the pioneering observation of Bregman made in the late 40s and fully developed to its full glory by Vilenkin and his collaborators, and also Wallach and his collaborators, is that special functions, at least the higher up to the higher transcendental ones, they arise as nothing else but matrix elements of representations of Lie groups. So one takes a classical Lie group, one takes some specific representation of the Lie group, computes some matrix element of this of pi of some group element, and then this gives you some special function. You run through all representations and possible Lie groups. You basically exhausted all possible special functions. Just to give you an example how it works, if you consider the motion group on the plane, so it's composed of rotations and translations on the plane, and you consider its representation on the space of square summable functions on the unit circle. So a group element of this motion group on the plane, it consists of a rotation with angle theta and translation of modulus r, and angle with the OX axis by phi. And then if you take a natural basis of this space, say given by Fourier coefficients for the ENs, you can construct a representation of this motion group, which depends on some external parameter rho, such that if you evaluate this representation on this group element and maybe dress it up with some factors depending on theta and phi, which enter in the parameterization of the group element, then you get exactly the Bessel function of the first kind, whose representation, integral representation I show here. But this actually interpretation is not just limited to higher transcendental function. Actually, you have really the same thing for functions in the Pain-Levé class. Maybe like the most prominent example is the tau function of Pain-Levé 6 equation, as it was pioneered by the works of the Kyoto group, also further developed by Oleg Lisovy and his collaborators. This tau function is nothing else but a 4-point function of a product of 4 vertex operator in a C-1 conformal field theory. So you should evaluate the vertex operators at some specific points in the complex plane, and you should assign them some appropriate scaling dimensions, and then you really fall on this some specific tau functions of Pauli 6.
Is it correct?
Sorry?
Tau function is infinite series of 4-point functions, 4-point conformal blocks, no? I'm not a specialist, I'm just wondering.
No.
It's not a conformal block. Or maybe I'm wrong.
No. Yes, it will be an infinite series of conformal blocks,
series of 4-point functions. Absolutely not 4-point function conformal block.
No. I think it's a series of lower conformal blocks, but you start with the 4-point function.
Okay, I'm just asking for.
But definitely, I mean, if you would do an expansion of this object in terms of conformal blocks, you get some series representation, and in the end, basically, this object is a Fredholm determinant. Yeah. But okay, so this is one kind of example. You have actually, if you consider correlation functions at the free fermion point of quantum integrable model XXX model, Sinh-Gordon model, nonlinear Schrödinger model, you get various other Pauli transcendents. For instance, like if you consider the quantum field theory behind the Sinh-Gordon field theory, so here I remind it's a classical evolution equation, you can compute it at the free fermion point, which corresponds to G = 1, coupling constant. If you compute 2-point function of exponents of the field and set G = 1, then up to a multiplicative constant, you have tau function of Pauli 3 equation, which is evaluated at R being this Euclidean distance of x to t. And basically now, what is actually a quantum integrable model? Well, it's realized as a representation of a quantum group, and correlation functions in this model are nothing else than taking representations of the quantum group and computing their matrix element in some vector of the representation space. So really, correlation functions outside of the free fermion point, they really end up fall into this classification or interpretation of special functions, but with higher algebraic structures being now quantum groups. And the quantum groups for free fermion equivalent quantum integrable models are very special because they are given by the deformation parameter q = I, so they are relatively simple, and that's what explains why the correlation functions take a relatively simple form, which is still in the Pauli class. So then, well, naturally, at least by studying these correlation functions, you get a way to construct many objects which you can really think of as special functions. So in particular, for the 2-point function in the Sinh-Gordon model, if you now consider an arbitrary value of the coupling constant, you get a 1-parameter deformation of the Pauli 3 tau function. And then you can do, in certain cases, you can do asymptotic analysis of the behavior of such correlation functions. For instance, in the XXZ case, where the free fermion point corresponds to Pauli 5 equation. And there you see from the asymptotics that actually the structure of the asymptotics in this case go, for various reasons, way beyond what you can hope to obtain in a Pauli class. So in this way, actually, the correlation functions of quantum integrable models, they provide you with really the next level of special functions. But then if you want really to speak about these special functions, you need to have well-defined representations for them. So in particular, you need to say that the convergence properties of the series of multiple integrals you have for the representation converges. Okay, and then maybe
I'm sorry. In the last in this.
Yes.
I'm not very polite. Could you please repeat give us a resume for this transparent? These are your fantasies or any results concerning the G nodes free fermion?
Yeah. So of course, I mean, so
general words, what we expect, or do you have any result concerning to these last line and previous line?
Okay, so I guess, I mean, what I'm saying here is like a vision I like to have of the theory of correlation functions in this model. So of course, correlation functions have already been very well studied. So in particular for 2-point functions of So what I try to advocate in this slides is that really, if you study correlation functions out of the free fermion point, then you obtain objects which go way beyond the Pain-Levé transcendent class. They have much richer properties, and like some of the results which were carried out in the example of the XXZ chain point you toward this richness of properties. Now, regarding to the existing representation, so in particular, like if we would focus on the Sinh-Gordon case, there are closed expressions for 2-point functions. I think the like 2-point functions of exponential of the field. So in particular, you can write them using representations proposed by Lukyanov for the free field construction. You can write them using representations which are of completely different type, which were proposed by Karowski, Babujan, and Fring and Zapetal. There are other representations for the these 2-point functions which you get from representations for the form factors which were obtained by Fedosmenov and also in his pioneering works, but also later Fedosmenov, Jimbo and Miwa. So definitely you have representations for the XXZ chain. There's really lots of representation for static and dynamical correlation functions, also for the nonlinear Schrödinger models, and also for many other quantum integrable field theories. I think ON models.
I don't understand. If you have Pain-Levé 3,
yes,
N for XXZ, for Sinh-Gordon, for XXZ correlators, what is the deformation of this guy?
Then yes, okay.
Yes.
This is of course
philosophy or any exact results.
So the deformation is that no, so that there are no. I mean,
what is the equation? What is the equation?
This is the point. I don't think there is any more differential equation which is
okay.
simple.
Then in which sense this is deformation of Pain-Levé?
Because you have a function which when
generalized Pain-Levé 3.
Which is a one parameter deformation of Pain-Levé 3. It's a smooth.
But what function do we have? Any ideas how to go?
Well, you take like the results of say a free field construction of Lukyanov, and then you have a series of multiple integral representation which depends on the coupling G, and then that's all you
this theory satisfied, right? Okay. Maybe I am asking too naive questions. Maybe I'm disturbing your talk, but this is very important question with Misha thinking for many years, but we don't understand. But maybe
no. I mean the kind of the best you can have is a closed expression in terms of, say, form factor sums. So you compute form factors for the Sinh-Gordon model at general coupling constant. It reduces to Pain-Levé 3 for G equal 1.
Okay, got the point. Okay.
And that's all. And precisely what makes that these special functions go beyond the Pain-Levé class is that you cannot hope anymore to have a differential equation which would describe, at least in a very simple way, like a differential equation like Pain-Levé 3, which would describe this correlation functions, because these functions, they have a really wild dressing of their asymptotics. So like in the Pain-Levé case, you have an equation which has some simple parameters in the equation. And for instance, suppose you know the behavior at 0 of the Pain-Levé transcendent, you want the behavior at infinity. Then the behavior at infinity will be given by a simple transcendental function of the parameters in your Pain-Levé equation. Now, if you consider such correlation functions in the general interacting case, well, you still have simple coupling, like the coupling constant, maybe some other parameters you have in the model, but then the short distance behavior, say, will be very, very simple. You want to look at the long distance behavior, and then the long distance behavior, you have some constants which are rewriting of the original constant in your problem, coupling constant, other free parameters, but then they are given by solutions to non-trivial Fredholm linear integral equations. So you already actually need Pauli transcendence to describe the constants in the asymptotics, or functions in the Pauli transcendent class. And this is somehow the reason I at least I cannot imagine how a differential equation would be able to do such a complex.
But there is no go theorem.
No. Of course, there is no go theorem. And maybe what I can comment is like there were early approaches based on dual fields for correlation functions in the XXZ chain by Nikita Slavnov, Isergin, Korepin, and maybe some other people, where they were trying to write precisely differential equations for correlation functions outside in interacting models. They could write some differential equations, but you still needed to average this differential. The differential equation was taking value in some operators in the Fock space, and you still had to do some Fock space average. So then it was not really giving rise to something tangible, I would say.
Okay, thank you very much. I'm sorry for disturbing, but
no problem.
The question was really, how to say, one of the most problem which we are discussing many years, and they could not progress. Okay, thank you.
No, but it's a very, very, very hard problem. So maybe what I would just try to say in few minutes is to give you the flavor of what you can do to prove convergence. Actually, it's something that is very closely related to techniques. You can inspire yourself from techniques which were fruitful in the study of random matrices. So, like, if you consider a set of random matrices, say Hermitian, quaternionic Hermitian, or symmetric matrices, in some potential V, basically you can reduce the study of this of the partition function of such a random matrix model to the integration over the eigenvalues of such matrices, and you get an ensemble which is a product of van der Monde to some power beta. Beta can be 1, 2, or 4 in the case of random matrices I mentioned, and you have an external potential e to the minus n v of lambda. And then the overall idea is you're interested in the large n behavior of such an n-fold integral. What is the overall idea? Well, you have a two-body interaction which is repulsive. So it's roughly, for typical distribution of integration variables, it is some constant to power n squared, because you have n squared terms, and you have a confining potential which goes like e to the minus n times v. So you have n terms. V is typically of order 1. You multiply by n because you have n terms, so it's something like e to the minus a constant n squared. And then what will happen is that the integral would be an equilibrium between repulsive nature and confining nature of the potential, and the equilibrium will typically take place at scale n squared, because this is how more or less your integrand scales in. So going beyond this kind of heuristics and really developing a rigorous way to understand it took an incredibly large amount of time, probably like something like 40 years. There were many people involved. So maybe not go through the developments, but basically the idea is that you can write the integrand of this multiple integral as the exponent of minus n squared times a functional which is evaluated, what is called the empirical measure. So empirical measure is nothing else but the probability measure on R, which is given by a sum of Dirac masses which are centered at the integration variables lambda 1 to lambda n. And the energy functional is integral of, so it's a functional on probability measures, which integrates the probability measure with V and integrate the logarithmic repulsive interaction with versus the square of the probability measure. And one has to impose that you don't integrate on the diagonal, because otherwise you get just 0. And then, of course, the natural idea is, well, if n is very, very large, then you can approach by sums of Dirac masses any probability measure. So then the integral should localize at the minimum of this functional on the space of probability measure. And this is now a theorem well understood in the framework of concentration of measure techniques and large deviations. So basically, the leading asymptotics are described by a minimization problem of some functional living in the space of probability measure. You can show that the minimizer is unique and it satisfies some singular integral equation for its density. It's supported on some compact union of compact intervals whenever the potential is reasonable enough. And actually, you can even solve the singular integral equation describing the density of your equilibrium of the minimizer of this functional by solving a scalar Riemann-Hilbert problem. And then you determine its support, at least theoretically, by solving some additional constraints. So there is a clear path to understanding n-fold integrals. Now, in a certain sense, the multiple integral which arises in form factor sums, it has is philosophically at least a similar structure. You have a one-body confining potential, like here. Then you have two-body repulsive interaction, because the interaction, like the exponent of the interaction, goes to 0 when two variables approach each other. So this is the two-body interaction. Actually, if you would have one and two-body interaction, you can just apply the setting of which was fruitful in the random matrix setting. Maybe you need some generalization, but it will go more or less okay. But then you have many body interactions. And this is a problem because you couple everybody with everybody. But then the idea is that you look at the expression for this coupling term, you do some upper bound, which is actually not so bad, because if you morally you expect that everything will behave like the exponent of a Gaussian in n. So if you bound by things which even grow to infinity slower than a Gaussian, it's fine. So you can write such a kind of bound for Kn. And when you write such a bound, you actually write Kn as a sum of functions which are product of functions of just couplings of two variables. You do some combinatorics with it. It's not so relevant, but basically the bottom line is that you can bound the original integral by an integral which is already much close in spirit to the ones appearing in random matrix theory. You bound it by some by a maximum of n+1 n-fold integrals. These are integrals which involve a two-species random matrix. You have two integration variables which are confined by some confining potentials. They have two-body interactions in between each of the integration variables and some interaction between the two types of the integration variables. This coupling between the variables is really due to the presence of this Kn function. So you have closed expression for all these integration points. Now, the main difference with random matrices is that here in the random matrix case, you have a scaling with n, because basically you want to put the potential at the same order of confining that the deconfinement produced by the two-body interaction. Here you don't have this anymore. So you have to rescale variables to go to the right scale. But when you rescale, you have some n dependence everywhere in your integral. So this is the first difference maybe with random matrices. Well, so lack of scaling of one-body interaction. So you just have an n-dependent one-body potential, n-dependent two-body potential. So you put it in this form, and then you try on this level of such an n-fold integral to apply ideas which were fruitful in the random matrix case. So if you apply the setting of concentration of measure techniques, you can, which were basically developed with Gaëtan Gouraud and Alice Guillonnet a few years back for integrals having n-dependent interactions. You can then bound this original integral you want to estimate by the exponent of minus n squared, the infimum of some functional on the space of probability, on the square space of, Cartesian product of two probability measure spaces. But this functional now depends on n. It has some closed form. It's quadratic in the measures. You can actually already explicitly characterize the minimizer of this functional by solving Riemann-Hilbert problems, but they are highly dimensional, so it's better to reduce the problem. You can lower bound this functional by yet another functional, which is now just depend on one probability measure. And basically what you get is that the n-fold integral is bounded by e to the minus n square, some n-dependent functional on the space of probability measures on R evaluated as its minimizer. And you need to describe the minimizer, fully characterize it, show how it depends on n, evaluate the n-dependent functional, and estimate how this n-dependent functional grows with n. So again, with my co-authors, we determine general properties of such minimizers. So you can build on that, and then to really thoroughly characterize the minimizer, you need to you need to solve a Riemann-Hilbert problem, but this time matrix valued, because you need to because what you have is that the measure which gives you the minimizer of the functional, it satisfies a singular integral equation of truncated Wiener Hopf type. So these are invertible by solving Riemann-Hilbert problems. The problem depends on n. But we have a technique called the Dive-Schuh nonlinear steepest descent, which allows you to analyze the large n behavior of solutions to such Riemann-Hilbert problems. So then if you apply all that and do some calculations, you can just do all the estimates. You have some very precise closed expression for the density of the equilibrium of the minimizing probability measure. You know precisely its large n expansion, and then from this you deduce the large n expansion of this minimizer appearing in the upper bound, and then you get to the constant I showed you in the theorem. And in particular, you see that this minimizer here can go to 0 with n, so it's very important to have an explicit evaluation of the leading asymptotics of the minimizer. It goes like 1 over log n to the cube. And maybe I stop here. So what I showed you is the setting up of a method inspired from random matrix theory, which allows you to prove convergence in the case of the Sinh-Gordon quantum field theory. So to do it, well, one had to kind of join many techniques which were appearing in the literature. So like probabilistic concentration of measure techniques, Riemann-Hilbert problem, but also some results from potential theory to characterize these probability measures, and carry out some soft analysis techniques, because in most of the cases you cannot just abruptly bound, but have really to be fine about the bounds. And then where I would like to go further is to prove precisely convergence for the Sinh-Gordon quantum field theory in the first place, which is a very good test if the method generalizes to more complex model, and if it does, then to attack the case of the lattice quantum integrable models like the XXZ chain. So thank you for your attention.
Thank you. So, excuse me, could you please repeat the argument where the p less than n appears, this estimate?
Sorry, which?
Earlier, a little earlier. The next slide. Here you have some.
I see. Okay, I see. Well, basically it follows from this part. So you have a Kn function, and you want to bound its modulus square. So well, you basically what you have such a geometric bound for L1 versus L square norm. So then you get the prefactor, which is a constant to the power n, but as I said, because everything would go roughly on a Gaussian scale, this is not so important for the asymptotics. And then you sum up over still these choices of integers L between 0 and 1 of something that couples two variables beta A minus beta B, depending on the difference, LA minus LB. Now, LA and LB are integers which are either equal to 0 or to 1. So if you really want to have a non-trivial coupling between some non-trivial factor between the two, you need to be in the situation where LA is 1 and LB is 0, or LA is 0, LB is 1. If both are equal, the numerator simplifies with the denominator. So for a given choice of LA and LB, you can partition the L's like the first L's L1 to LP are equal, and LP plus 1 to Ln are equal. Then this double product will not cancel, only for where you have couplings between the first p variables and the remaining n minus p variables. And this is the origin of this parameter p in this in this bound. And here you see really the two-body coupling, which stems from this non-triviality added of the coupling added by Kn.
Okay, thank you. Thank you.
Karol, I'm sorry, I did not understand absolutely this sophisticated part. But could you please tell me a simple question? We have minimal form factor squared. Mm-hmm. Minimum form factor is double sign, rather complicated function with double poles, etc. Mm-hmm. Where it is in your construct, I don't see.
I see. So minimal form factor is this
in exponential.
Yes, yes.
And you can using matrix model result somehow simplify its contribution, or
no, you explicitly evaluate its contribution. You actually if you use Riemann-Hilbert techniques and some input of potential theory, for instance, if you don't have Kn, for any value of the function W, you can extract large n asymptotics of this integral.
So your problem is about this polynomial part. I mean Kn part.
Yes, because one needs to bound it.
About this.
Yes, one needs to bound it in an appropriate way to be able to have something that goes to zero. If you bound it in the wrong way, then you don't get a good bound for the integral.
But the referring to matrix model result was essential for your result, or you can give us mathematically rigorous result without reference to any. Okay.
I mean, well, maybe I referred to matrix models because this is where this idea were born in the first place.
Okay, the idea was borrowed. Okay. Because I definitely know since Fedor-Smirnov's first papers, everybody asked, "What about convergence?" And we all answered, "Nobody knows." Okay, then you are given the proof. Great.
Thank you. But basically, the tools you need to know is concentration of measure, which is a way to think about saddle point approximation in infinite dimensional spaces, and the Riemann-Hilbert problem, which allow you to solve yes, because you reduce like estimation of integrals to finding minima of certain like, for instance, in the matrix model case, minima of certain functionals on spaces of probability measures. And for this, you need Riemann-Hilbert problems to be able to thoroughly characterize the minima.
And what about your understanding of two-point correlation function after your advance? Can you say something new about Sinh-Gordon correlation function? Any
No, I am thinking on this, but for the moment, no, not so much. I mean, I have some understanding of the XX. I think now XXZ case I fully understand all the regimes, but somehow the structure of series for Sinh-Gordon are a bit different. The sort of contributions and type of saddle points which contribute to the short distance asymptotic is quite different. So for the moment I have no clue. Okay, but it's definitely a very interesting question to me.
I guess it would be interesting to analyze convergence on the, if I'm not mistaken, a semicircle of the constant G, connecting the Sinh-Gordon model with the free Fermat model in Sinh-Gordon region.
Oh,
maybe some problems there.
Yeah. Probably there might be some problem because kind of the techniques I use, they are strongly building on real valuedness of the integral. So somehow I can bound by absolute values and things don't get so bad. But then if one starts to do analytic continuation in the coupling, then everything becomes complex valued. Actually, so far there is no appropriate saddle point techniques like equivalent of nonlinear steepest descent in this infinite dimensional setting. So
that would be a challenge.
Yes. But definitely this would be very, very interesting. I haven't thought of this problem, but I definitely see now its interest.
Oh, okay. May I ask a short question? So for square root of one, for the simplest root of unity, we kind of have some explicit representation, determined representation, some relation to the equation, whatever. Is there any chance to expect that for other roots of unity will be some simplification, probably?
I think. So for the case of the XXZ model, so there is like well, second root of unity is the free fermions, and third root of unity is the so-called combinatorial point, and there you have quite a few specific results. In particular, you have many results by Rezumov and Stroganov, who unraveled some very non-trivial combinatorics in the structure of the ground state of the model. Also, for certain correlation functions, they can be computed in closed form, in particular the so-called emptiness formation probability. In that case, actually, you have a strong connection with enumeration problems like enumeration of alternating sign matrices or alternating sign matrices with different additional constraint on the matrix. But then for other roots of unity, I don't know. When one looks at expressions like for the XXZ chain at those roots of unity, there's definitely some algebraic structure which is more algebraic structure than in the general case, but still, I think nobody managed to do something with this.
Speaking of form factor expression, there's this higher, the high level of transcendentality. Where it comes from? Does it come from the fact that the minimal form factor is an infinite product, so it has infinitely many zeros and poles? That's the reason, or?
No, I think that the main reason is because that you could still live with this in a certain sense, but the reason is that the form factors do not have any more a closed simple determinant expression, so they really couple in a very non-trivial way all the integration variables. So it's somehow really something that is due to those functions Kn, which are here, and well, of course, I mean they don't couple in a completely wild way. There is some structure to that, which then makes it a special function. But still, this coupling allows for a really non-trivial like modification of the asymptotics of these functions by dressing the original bare constants of the model through some solutions of linear integral equations. But actually, I would really like to know what's really like the part of the function which would determine the border between the two kind of regimes, and it's still unclear to me. Maybe not enough examples which went through.
Yeah, okay. So another question. Oh, well, sorry, about the 3D factors. If you, recent years it's very popular. I mean, these CAD factors in relation to TT-bar deformation. So as far as probably I'm wrong, you would expect some problems with convergence if you add random CAD factor in this kind of setup. Am I right? So, so can you comment how it happens if you know how it goes?
I think, but I think maybe in this case, like the S matrix is maybe you have some CDD factors or something like this, and I think that complicates the solution of the bootstrap program. So you don't have any more such a simple structure for the form factors, because like where is it? If I go back to the original expression for the form factor, basically the non-trivial building block is this kn function. And here you sum up over choices of integers from 0 to 1 to power n. So you have 2 to the n choices. It grows very fast, very slow. Like you don't sum up so many terms. So because of that, I could make like a simple bounds for the series. But if you would sum up through much more terms, and I think that's more or less what would happen in such a case, then yeah, things can break down. Also, I mean, what can happen is that the because like what ensures convergence is a kind of a equilibrium between the repulsive nature of the two-body interaction, so that the integration variables cannot come too close to each other, and the attractive nature of the interaction, which is this confining like potential, which tells you that you cannot run too far to infinity. So then what the potential does is that your integration variables, they have to stay close to each other to some in some independent volume of the integration domain, and then but this and then at that level you have a kind of compensation of how small this is and how small this is. But this compensation then can lead to a behavior which grows like exponential, or which decays like which goes like a Gaussian, or decays like a Gaussian. So if the two-body interaction is too repulsive, for instance, then yeah, the integral would just blow up with n. So I think actually also Fedor Smirnov advocated some problems of convergence in the O3 model. So maybe there's a similar thing, but
yeah, I mean, that's curious because sometimes CDD factors lead to UV complete theory. So I mean, if you tune them in like smart way, somehow you will overcome all those difficulties. You will still expect. Am I right? So that the convergence is kind of physically, it's related to the fact that your theory is UV complete, so you can kind of continue from large R to like 0. So it's kind of the convergence it's a property which you expect. For local quantum field theory, you expect the convergence. Am I right? For you complete local quantum field theory, you expect the convergence. Otherwise, it would contradict some basic principles. Something like
yes, probably that should be something like this. But well,
so, I mean, this what you're doing. You can treat it, as a tool for checking if. So you have like a random S matrix with some random series factors, and you might compute the form factors and check that this sum is convergent or not. If it's convergent, it might signal for that your S matrix corresponds to UV complete quantum field theory. Otherwise, it's certainly not.
Yes. But what can also happen is just that maybe the picture which is used for describing the QFT in itself it's well defined, but the picture used to define the CFT fails to be defined at some point. If you take like the analogy with the hypergeometric function, so for instance, like you would write it as a series expansion in powers of z. Well, in some cases it would have like a radius of convergence of 1. So you cannot just go beyond 1. But then you write Gauss integral representation, Mellin-Barnes integral representation of a completely different nature, and then you can continue this function somewhere else. So it can be that it's just that like for shorter radii at some point you need to resum the series and have another picture for understanding. So just maybe the expansion which is used to understand the Whiteman function is just not valid to some point, and you need to do some different representation.
Yeah, but numerics, I mean, numerics always shows that it goes all the way down to almost to r equals 0. So
yeah. Well, so then somehow, well, it should be possible to prove convergence.
So you're saying correctly. So the issue of convergence is contained in this p function, how we call it. So the number of terms in k matters. So it's exactly what provides you the convergence, or
yes. So actually, maybe not even the typical shape of K which you choose for would matter for convergence, and this is really fixed by the S matrix. So like you go to Sinh-Gordon, it's a matrix valued S matrix, and then already the form of K is much more complicated. It's a transform given in terms of multiple integrals. I still think that in this case convergence would work.
But it cannot be estimated a priori. It's only a posteriori. So I mean, first you compute it and then you estimate the growth. But you cannot go other way around. So just without computing, just to estimate the growth. No.
At least I wouldn't know where to start. But I think, like in many cases, like especially in 1+1 dimension, the existence of field theory is associated with quite general scalar potentials, scalar classical, quite general Lagrangians was shown to exist. Of course, there's no closed form for the Whiteman functions, but somehow there's an existence theorem, so which would point out that there should be some convergence.
I also naively want to ask Karol, could you please formulate for us very simply, how to say, very simple result of your talk, of your works for Sinh-Gordon, for any B, any parameter B, 2-point correlators expanded in form factors are well defined.
Yes.
What is?
Yes. So this is exactly the statement.
For real B.
For any real B, 2-point functions.
1/2 or any.
Yeah, I think up to 1/2, but
up to 1/2. 2-point correlators or n-point correlators.
2-point. Endpoint I didn't.
Are rigorously proved to be well defined as form factors spectral decomposition, right?
Yes, in the space-like regime.
To remember forever.
Yes, in the space-like regime. So time-like regime I still didn't consider, and
space-like regime. Okay. But I read this great achievement. Thank you.
Oh, thank you.
It means that this expansion defines you some functions. Well, that concerns equations. This
sorry, Lyosha.
The statement implies that the conform factor expansion defines you some function. That's a definition of the function of some high transcendental function.
No.
Generalization of Pen-Levitsyn transcendent.
K is arbitrary polynomial for descendants and primaries, right?
No, let's take just primary field. Then K is known. Then
yes, exactly.
And the convergence implies that this expansion defines you some transcendental function. This is the definition of this function.
Okay. And the proof is this series converges for any B less than 1/2.
Yeah.
Real B.
Yes, you have like a definition of hypergeometric function in terms of series. It has domain convergence, and in this domain it defines you the function. Here's a similar statement.
Okay.
2-point functions, as Karol said, 2-point function Sinh-Gordon is the highest of known levels of transcendental function because it contains like Pen-Levet transcendent in the special value.
Okay.
I think that's very. Yeah, and Karol, you also said that there's a way to, yeah, actually, can we just having the form factor expansion? Can we say something from analytics about the UV expansion?
So far, not so much. There was a work by Fedosminov who argued some form that it should go like R2, so the Minkowski distance of x to t to some power, and with some constant. He wrote some expression for the constants, but the constants are extremely complicated. So you would expect very simple numbers for these constants, but so far they're given by basically form factor series. So nobody really managed to simplify that. And there should be definitely a more direct approach to extracting the asymptotics, but so far it's not has not been done. I'm trying to generalize some techniques which I developed for the analysis of for asymptotics in the XXZ case, but the type of series is completely different. So for the moment, no really clue.
No other questions? Okay, if no questions, let's thank Karol. Thank you very much for
Thank you very much.
talk.
Oh, thank you very much for the invitation. It was with pleasure.
Thank you very much.